Hi everyone, my name is Craig Gutterman. Today I'm presenting Stallion, video adaptation algorithm for low latency video streaming. This work is in collaboration with Brian Freeman, Trey Gillian, Yusheng Hu, and Professor Gil Zussman at Columbia University. I'm presenting our proposed solution, Stallion, for the Twitch Grand Challenge, adaptation algorithm for near-second latency. Twitch has been successful in delivering ultra-low latency streams to millions of viewers, but to improve the live social interactivity of a broadcast, the goal is to decrease the latency even further. However, as they drive towards near-second latency, Twitch found that existing adaptation algorithms are not able to keep up, as smaller player buffers do not provide enough time to respond to changing network conditions. The purpose of this challenge is to design an adaptation algorithm tailored towards HTTP chunk transfer streaming in the near-second 1 to 2 second latency range. It should minimize rebuffing while maximizing bandwidth. Twitch provided a testbed against which to evaluate implementation along with network profiles which reproduce representative conditions. As part of this challenge, we're given the goal of designing a low-latency ABR algorithm. We are provided with a fork of dash.js modified to pre-request low-latency segments as well as a low-latency dash server. For evaluation, we were given 5 networking patterns to simulate different networking conditions. In addition, we were given a general QE model which combines the metrics of bitrate switches, rebuffering time, live latency, and playback speed. When I talk about latency of low latency, I'm talking about the live stream latency, or the end-to-end latency, or the hand-waving latency. It is defined as the time between an event being captured on the broadcaster side and when it is rendered for the viewer at the client. I'm not talking about the network latency or round-trip time between the client player and the streaming server, or the CDN. First, the stream is captured via a camera device to convert it into a digital format. Next, the stream is encoded to raw data files to ensure smooth playback when it's streamed over the network to reach its desired audience. Then the stream is sent to the streaming server, which is responsible to broadcast it to viewers to be able to access it. Streaming servers have to ensure low latency streaming by configuring segment size while delivering content and managing content delivery. The streaming server sends the segments over the internet to the client's live media player. While I draw the internet here, it also can exist between any of the other components shown. To load a video client periodically requests individual segments of video from a video server. Each segment presents several seconds of video and can be requested to have one of several bit rates. Here we have low, medium, and high. As the video segments are downloaded, they are stored in a playback buffer. As the video is playing, the playback buffer is continuously drained at a fixed rate since its users are watching it in real time. But the buffer will be populated at a variable rate depending on the requested bitrate and network conditions. To give us a picture of different ranges for live latency, we have a graphic from Wowza. Typical HGTV live latencies for large audiences are in the range of 18 to 45 plus seconds. If you want to reduce it more for some sports or news content, we might be able to get it down to the 5-second range. The 5-second latency range is what is typical for cable TV streams. The next level to look at is low latency. To maintain interactivity, feedback from viewers is needed to arrive to the broadcast within 1 to 5 seconds. Now we're trying to push that latency to the lower end of that range, so the 1 or 2 seconds of latency. This places a relatively tight constraint on media streaming latency. HLS, WebRTC all complement and have the ability for low latency, but there's a big trade-off between the quality and latency. If you want to have a higher video quality, it's better to have more data stored in the buffer. For example, 30 seconds to reduce the chance of the video stalling. But this means you will have at least 30 seconds behind the live stream. When we get to low latency and close to the near real time, requesting a high quality video comes at the cost of stability of the stream. Now I'm going to go through an example of how the target latency impacts the buffer value and also results in the stability of the player. The requirements for the challenge is they'll use segments of the video that are half a second long. And we have a target latency between 1 and 2 seconds. The example I have here is that we're trying to have a target latency of 1 second. In the figure below, we have one segment that just finished being coded at 3 quality levels, and only one stored at the player buffer. What makes this challenge difficult is that this already gives us the 1 second latency we're targeting. By the time a segment is complete, the first frame in that segment is as old as the segment duration. While the segmentation latency can be reduced by reducing the size of the segment, this would lower the video coding efficiency. Now the encoder and streaming server start sending one of the completed segments to the client player. The buffer in the player has decreased by 0.1 seconds, and the camera has collected 0.1 seconds of the next segment. But we can't send it yet because the segment isn't complete. The segment that's being sent has to arrive before the segment in the buffer is depleted. The segment is almost at the client, but but not quite there. But due to variations in the network, it has not arrived yet, and the player will now stall. Now, this is the one thing we're trying to avoid. It's very important to be able to choose the correct segment based on the estimated bandwidth. If you choose too high of a resolution, you might not have enough time to adjust and request a lower quality segment that could have arrived quicker. This results in the video player running out of the video in the buffer, and we get this annoying experience. The video suddenly gets stuck and starts rebuffering. Therefore, bandwidth estimation and buffer health knowledge are very important for low latency video streaming. ABR algorithms can be classified into three broad categories: throughput-based, buffer-based, and hybrid. Throughput-based algorithms work by estimating network throughput available between the client and the server. They usually rely on using a sliding window or expected weighted moving average. Some examples of throughput-based algorithms include Festive, Panda, and Squad. Buffer-based algorithms use the buffer level to decide on the bitrate of the next segment. Some examples of buffer-based algorithms include BBA and BOLA. Hybrid algorithms use both throughput and buffer-based algorithms to decide on the bitrate of the next segment. One example of that is Dynamic. Dynamic is the default ABR algorithm provided by the standard reference player dash.js, and the one we use for comparison. Here's an example from one of our test experiments. On the graph on the left, we have throughput on the y-axis and time on the x-axis. In the blue line, we can see that the throughput measured by the throughput rule in Dynamic shows the average throughput measured with a bit of slack to ensure that the player requests a segment that can be downloaded in the segment duration. Even though the measured throughput looks stable, there's quite a bit of variation in individual samples, the red dots here. And when the available bandwidth changes quickly, the individual segments change quicker. And if we overestimate the available bandwidth and the throughput with a lower buffer of 1 or 2 seconds, there's not much time to adjust. We can see that on the right-hand graph, the buffer level quickly goes to 0 when this happens. The average filter pays only attention to the mean, resulting in the system not reacting fast enough to network variations, causing stalls and variable bit rates. Although you may not want to adjust to each individual segment's throughput measurement, it is important to pay attention to the variation. Therefore, we designed Stallion to deal with unstable network conditions and pay attention to the fluctuations of throughput during playback. This type of measurement is not new for networking applications. For example, in estimating round-trip time in TCP, the deviation of round-trip time samples has been used along with the mean round-trip time since the end of the 1990s. Stallion is defined as standard low-latency video control. Stallion uses a sliding window to measure the mean and standard deviation of both the throughput, C, and the latency, L. Here, latency is measured as the time the request is sent to the time the first packet of the segment is delivered. Both the throughput safe measure and the latency safe measure have a safety factor, Z, that can be adjusted. When estimating the max available throughput, R, we have the safe throughput multiply the usable amount of time for the segment duration, which does not include the latency. Stallion relies on use of these measures to make a safe estimate for our bitrate selection, which will reduce the amount of stall events and improve the overall quality of experience of the end user. We use the dash.js player provided in the challenge to test the performance of ABR algorithms. Additionally, we implemented an automated system where we can log the performance of the player and analyze it. The system diagram in the figure shows the major components used for testing. The ABR controller uses statistics from the network and buffer level to determine the bitrate of the next segment. The default ABR algorithm for Dash is dynamic. This controller contains a dynamic ABR controller, which is a collection of ABR rules, including throughput rule, BOLA rule, insufficient buffer rule, switch history rule, and drop frame rule. The hybrid model dynamically chooses either BOLA or throughput rule depending on the buffer level. For Stallion, we replace BOLA, throughput rule, and insufficient buffer rule for our Stallion rule, which relies on the calculated sample standard deviation of both the throughput and latency for the sliding window. Stallion relies on the use of these measures to make a safe estimate for our bitrate selection. There are 5 networking profiles which are used for testing to emulate varying network conditions between the client and the streaming server. These networking profiles were given as part of the Twitch challenge. Each of these networking profiles has a set throughput limit and the length of time for that throughput limit. For example, for the cascade pattern, there are 5 periods starting from 1200 kilobits per second to 800 kilobits per second, down to 400 kilobits per second, back up to 800, and then back up again to 1200 kilobits per second. Each one of these periods lasts 30 seconds. All experiments were conducted on an Apple MacBook Pro laptop with a 2.8 GHz Intel Core i7 with 16 GB of RAM. Both the server and the Dash player were run on the laptop. The Dash.js player ran in Google Chrome browser. The video used for testing is Big Rock Bunny, and each video is encoded in 3 bit rates of 200 kilobits per second, 600 kilobits per second, and 1000 kilobits per second. The associated video qualities of these bit rates are 360p, 480p, and 720p respectively. Each ABR algorithm, Stallion and Dynamic, were both run for 20 times on each of the 5 networking profiles described on the previous slide. We focused on 5 metrics for our evaluation criteria, including selected bitrate, stall duration, live latency, playback speed, and number of bitrate switches. Overall, a QE metric was provided by the challenge that combines these QE metrics into one QE metric. A detailed description of the weights of each of these components is described in our paper, as well as the metric description shown in the link at the bottom of the slide. For each of the QE metrics, we have a box plot. For each box plot, the middle represents the median. The bottom of the box represents Q1, and the top of the box represents Q3 of the dataset respectively. The first metric we look at is the average bit rate. It's highlighted here in blue. On the left-hand side, we have dynamic, and on the right-hand side, we have Stallion for each networking profile. For all 5 networking profiles, dynamic has a median bit rate less than 300 kilobits per second. The median bit rate for Stallion, on the other hand, is greater than that for every networking profile tested. Overall, the average bit rate increased from 290 kilobits per second to 530 kilobits per second, 1.8x increase in average bit rate. We analyzed the stability of the playback based on the number of playback rate switches, highlighted in the graph in orange. The performance of the both ABR algorithms tested is approximately the same for spike and fast jitters. There are approximately 2 additional switches in Stallion compared to dynamic for cascade and slow jitters, and intra. Each ABR algorithm has a median number of switches less than 10 for each networking profile. For dynamic, the target latency is set to 1 second, while it's set to 1.5 seconds for Stallion. This plot shows a performance improvement for dynamic over Stallion, as it has a greater than 0.5 live second latency less. Stall duration is highlighted here in green. This is one of the main issues that can occur during near-second low latency playback. Is the number of stall events and the length of time the video is stalled. We can see significant improvements in the length of stall duration for Stallion over dynamic. For example, for Cascade, there's a large improvement in stall duration, as dynamic has a median of 22 seconds, while Stallion has a median of 3 seconds of stall duration. Across all 5 networking profiles, there's an average stall duration of Stallion is 3.1 seconds, compared to an average stall duration of 13.3 seconds for dynamic. This is a 4.3x improvement in average stall duration for Stallion. The final individual QE metric component we investigate is the absolute playback error, highlighted here in purple. The absolute playback error is calculated as the sum of the playback error for each video segment of an experiment. As the video stalls, the playback location falls behind, causing the player to adjust its speed to catch back up. As a result of the increased stall events for dynamic, the dynamic playback error is significantly higher than for Stallion. For Stallion, the absolute playback error is kept below 5 for all experiments, with a median of 1.37. The overall QE performance combined is shown on the box plot on the right. Stallion outperformed the QE in all 5 networking profiles. The profiles that saw the biggest improvement were Cascade and Intra. The challenge goal was to develop and test a low-latency ABR algorithm for near-second latency. This led us to developing Stallion. The design of Stallion used information provided by the simple second-order metric standard deviation of both latency and throughput to make safer decisions about the requested segment's bitrate. These safer decisions allowed Stallion not only to reduce the number of stalls considerably, but also improved the bitrate without significantly increasing the number of bitrate changes. Stallion shows a 1.8x increase in bitrate and a 4.3 reduction in the number of stalls compared to dynamic. Overall, Stallion has improved QE for near-second low-latency streaming. Beyond this challenge, we'd like to take the knowledge we learned and expand on this research. We plan to test additional network profiles, improve the safe estimate bitrate, as well as add a machine learning system to auto-tune Stallion parameters. I'd like to again thank my fellow research collaborators, Brian, Trey, Yusheng, and Professor Gil Zussman at Columbia University for their important contributions to the project. If you have any questions regarding this project, please feel free to reach out to me at my email, clg2168@columbia.edu. Thank you very much.